So this talk is very much meant to be a pedagogical introduction to people who do not know about double and exceptional field theory and geometries. There are many experts in the audience, so you can continue with your laptop and so forth, because I'm sure you'll understand everything I'm about to say. It's going to be very non-historical, in the sense I'll make no attempt to describe how historically it came about, but instead give you a very, well, a different perspective in some sense. And then hopefully we'll get onto the notion of more mathematical structures, but I'm going to start out in a very, how should I put this, simple and basic view, which is starting with the idea of Kaluza-Klein theory, which you should all know about, but let's go through it a little bit. Okay. If you cannot hear me, or my writing is too small when I begin, do shout. Okay, so let's start with Kaluza-Klein. Is that a good sized handwriting? So, of course, we had 4D, Einstein, Maxwell, with the fields in the theory being the metric in some one form. Of course, there was some action, which we all know. This Einstein Hilbert. And the question which Kaluza and Klein asked themselves is, can you lift this to a single geometric theory where, here I should say, importantly, we have local symmetries, which are diffeos, and one-form gauge transformations of A. Gauge transformations. So, can we lift this so that we have a single geometric object in higher dimensions where the local symmetries are combined into one thing, and the fields, G mu nu and A mu, are combined into one thing, and then we have a simpler action functional, again, of the combined object. So, of course, the answer is yes. The key observation of the thing is that we can add one dimension. So, where previously we had coordinates, so now this is a four-dimensional space, and I've introduced some coordinates, additional coordinate x5, and then we can have our metric on this space given in terms of the fields here combined into one five-dimensional metric. I'm not going to deal with things like dilaton factors and R's, but let's just leave it like this for now. And then crucially, the 5D diffeomorphisms become equal to 4D diffeos and gauge transformations. If there is a constraint which is that the generator of the five-dimensional diffeos is independent of x5. So then you would have V mu 5, which is our generator of 5D diffs, is given by V mu of x, not x5, and chi of x. Okay? So it's a very simple thing which says if I wish to combine 4D diffeos and one-form gauge transformations, I can do so by having 5-dimensional diffeos and a constraint. And then, because then this should be a single vector, I need to add a dimension. And then I can form a metric in that higher dimensional space, combining these fields. And then, if I have this constraint again, the action will equal this one. So this is what we know.
Is there any trick to make this global? Because
at the moment, very good, and I'm coming to global questions. At the moment, there is nothing which says that this extra dimension, we're going to discuss this, is compact. There is no information about the global structure at all in what we've just done. And that's because I'm not interested, well, I'm only dealing locally in terms of diffeomorphisms, not globally. So these are infinitesimal things with the derivative, with things like this. And yeah, so I only see the local things. In a moment, I will discuss global things. Traditionally, you're told Kaluza and Klein, you require that x5 is compact in a circle. Now, there are two reasons to do that. One of them is that you require this constraint to emerge as a low energy effective approximation. So that if R is small, then we can go into the infrared on the other space, then we can ignore the field dependencies on x5. I don't want to do that. I'm not going to mention that. You maybe mention it, I regret it. Instead, we're going to look at the quantum theory, and that will tell us why this should be a circle.
I mean, also from geometrical perspective, because you have a global object, the metric, you combine it with a local object.
Yeah, so I mean, you want me to, yeah.
Okay.
Yeah. No, yes, go on.
Yeah, also if you want the large gauge transformation, you will need
Exactly. I mean, that's what I said. Writing this is not large, but that's all I've done so far. But let's start with this and then we go. I've not factored in the talk the time it takes for the board to go. Okay. Right, next step. It's not enough for me in my theory that I have Einstein-Maxwell. I want to have charged objects. Okay? As this, just in this theory here, this would not have charged objects. This would be Maxwell theory without charges. So now I want to have electric charges. Okay? And these come from momentum in x5 direction. And so you can do a quick calculation to show that Q, the charge corresponding to that field strength, which is equal to star F, is equal to E5. Okay? And in fact, these charged objects are BPS. And a null Q is equal to mark P5. Okay. So it's BPS in the sense that the electric charge is equal to the mass. Charge equal to mass in that sense, it's half BPS. And that's really coming from the fact that the natural half BPS object is always null. Okay. Now, at this point, as I said, P5 can be anything. And that's because we're only sensitive to the algebra. But if we require charge quantization, so it's not sufficient that I have electric charges, I should also have quantized electric charges, then this implies I want P5 to be quantized. Which implies X5 is identified 2 pi r, and then P5 is some integer over r. And then we get the compactness of the space from demanding charge quantization. Okay, that's fine. Next step. I'm not happy only having electric charges. I want to have magnetic charges. So next, magnetic charge. So now we've got to do really some global structure here. So what I had locally in this construction was that my 5-dimensional space was R4 cross S1. And in fact, when we've got this usual Kluser-Klein setup, we think of this as being globally true. To construct a magnetic charge, we say that this is only true locally. So we fix the same local patch, and it has the same Kluser-Klein metric ansatz. But actually what we do is we write R4 as being equal to RT, take time out, that's just the time part, cross R plus cross R3, S3. That's not adding up 3 or 5. R5 like this. Because this S3, we can of course write as a Hopf vibration, so that locally this is S2 cross S1 locally. Okay? So I do the Hopf vibration of S3. So that then we end up with time R plus cross S2, and this looks like R4, but now this is really fibered. Okay, so this is going true locally, this is our fiber. Apologies, this is all stuff you know. Just keep at it. So in other words, we know that the monopole is given by a Hopf vibration of S3, and then in the Kluser-Klein setting you can do that, and all that does is make this product structure local, and then we allow ourselves to have twists of that S1, and then that gives us the magnetic charge. So then G, the magnetic charge, is equal to the integral over that S2 of F, and then that is equal to an integer, maybe with some 2 pi's. Okay. So the reason why I'm emphasizing this is that even if you've done Kluser-Klein theory, you can get things you might not have thought of by doing local patchings and giving yourself a vibration. Okay. Right. How does this get extended? Of course, we can go, once we've done this trick once, we can go to higher dimensions. And there's not much more you gain than the obvious, apart from what, so then we would have R4 plus some d-dimensional manifold, and again, let me put coordinates in this thing of y, let me call these coordinates on here x. And again,
sorry, can I ask a question?
Yeah.
So where does this number m come from in theory? I mean,
Yeah, so this is the first Chern class
But it's
of the Hopf vibration. That's what you measure when you do this integral. And the first Chern class is quantized.
So you remove the origin from R4.
Yeah. Well,
Yeah. Not after R3.
I mean, it's the fact that I've got here a natural S2, which is the, I mean, here what I've done is gone to polar coordinates on R3, time is ignored, then I've got the S2, and then I've got the circle, which I then twist over the S2. I measure that twisting, that's quantized, topologically the only way you can do it, and that gives me an integer, which is the first Chern class. You know, the S1 bundle over S2.
But if it's S3, that's just 1, right?
Which is S, yeah, so if it's S3, this is 1. So, yeah, okay. Even better. I've done a single. Absolutely. Absolutely. Okay. So, you can get higher dimensions, you can have something like this, and then this would be the Kluser-Klein, traditional Kluser-Klein constraint. But you can do a little bit more. You can do a bit more, and what I mean by that is that what's important in this reduction, in this constraint, is that the y dependence of the additional space doesn't appear. So what you really require is that the four-dimensional action is only given with some Lagrangian that only depends on x, not y. And actually, this does allow you to have high-dimensional spaces that depend on x and y, and in fact this can factorize, subject to the constraint that when you put it into the Lagrangian, the y dependence is removed. So this goes by the name of, so, is allowed, provided L, the Lagrangian, is only a function of x with that particular ansatz. Okay, so this goes by the name of Schwartz.
So can you explain your notation for your constraint there?
Yeah. Here,
Yeah.
I've just got,
What's the dot? What's
Yeah,
the
yeah.
dot of the dot?
so I've just got, I've written here some generic set of coordinates y on this manifold, which we're extending this space by. And I'm just saying that the usual Kluser-Klein thing is that all the fields in the theory, whatever they may be, will be independent of the coordinates.
Okay.
But then there is this additional idea that actually this may be too general, that what you really care about is that y does not appear in the final Lagrangian. So if you have a specific enough form of G, your initial ansatz, then actually this can be too strong. And this will allow you to do things like, S3 or S7 reductions. Obviously, S3 and S7 have a metric, which depend on the coordinates on that space, but actually they're such that you can reduce it like this.
Excuse me?
Yeah.
Is it possible to reformulate this as some differential conditions in the y variable such that the L becomes a closed form in the
Yeah, you can do all sorts of things that way. if you're more sophisticated than that. Okay, so far, I don't know, all of this has been done from Kaluza and Klein in the 1920s. I guess the Kaluza and Klein monopole, though, was only done by Gross, Sorkin, and Perry in the 1980s. But, you know, and then Schwartz reductions were big in the 70s and 80s, where we looked at different sorts of compact space you can have and what the necessary constraints were. So now what do we do? So now I guess this is where we go higher in the theme of the conference, which is that this was all very well when I began with diffeos and one-form gauge transformations. The question that we're now going to ask is, can we do Kaluza-Klein theory for diffeos and two-form gauge transformations? And then eventually we'll ask the question, diffeos and p-form gauge transformations. And what I want to do is exactly follow through this set of reasoning, where first we will look at the combining symmetries. We will look at then say, okay, can we then have a combined object of the fields? And then can we form an action? And then where are the charges? And then are we allowed to form magnetic charges, which are twists when we've created this additional set of dimensions? Okay. So let's do that. I can save time by not moving forwards. There's one way to burn off breakfast. Now, you know, people could have asked this question, and I'm sure some people did at the beginning of supergravity. So the low energy effective action of the superstring in its most basic form is given by the NS supergravity just has, let's go to dilettante. I mean, we're in dilettantes throughout this. Let me ignore dilettantes confused. You can put all that in, but it's going to confuse the story. We've got our metric and our two-form. We've got our action in d dimensions, Einstein-Hilbert. Three-form field strength. And, of course, apart from diffeos, so our local symmetries, and two-form gauge transformations. Okay? So, what you'd want to do, and I'm sure people thought about this, especially because from the string perspective, G and B come from the same level of the string. But you know, you've split the space up. You've got G describes some background geometry, H sort of you think of as living on the space. I've got these different fields, I've got these very different sort of gauge transformations. But you can ask yourself, can I lift this thing a la Kaluza-Klein? Can I add dimensions and make these two seemingly very different local symmetries part of one bigger thing? So, let's see how far you would get. Well, the first thing that we want to do is looking at the local symmetries. Let's look at it. So diffeos are generated by vectors. And then this is generated by one forms. So I want to make a generalized vector which I will call U, I, which we made up out of mu, and then some one form, chi within x down, it's a one form. Okay? So all this is doing the most simple thing, which is saying the most basic data I've got is a vector for diffeos and a one form for gauge transformations of two forms. And then I combine them into a single vector, the idea being that I will use this to make a generalized diffeomorphism as generated by this object. Well, if I've now got a vector that's 2D dimensions, I better extend the space, not by one dimension, that obviously won't do it. That did it for electromagnetism, where I only had one new scalar degree of freedom. I'd better instead extend my space-time with 2 dimensions. Sorry, we have to double the number of dimensions. So here, I now need to add d dimensions. Okay. So do you see the reasoning? I want to get these one-form gauge transformations as part of a vector in this bigger space. I better add d of them. So now I've got d sets of coordinates. I can then construct the equivalent of a Cluser-Klein metric, KK type metric, on this space, Gij, which combines the 2 form and the metric
The head now is I.
You're right. That's, yeah. Thank you. Let's stick with that there. So this is our 2D space. This was our original space. This is what we've extended by, and this is the metric on the extended space. And this is exactly the same as a Cluser-Klein ansatz. Though here I've done something funky. And I'll come back to why this works later. So the next step that you would do is you would try and construct an action for this object G such that under the constraint that nothing depends on x tilde, you would reproduce the Never-Schwarz action over here. Okay?
Excuse me?
Yeah.
What contract synthesis between the
Little g. Yeah. So here I've just raised, this is short for g lower raised with. Yes. So then we want an action. Now, I think at this point, people, I suspect, may have well tried this game if they did Cluser-Klein theory in whenever. And then they got to this point and went, you know what, that's Cluser-Klein ansatz. And then you put in S Einstein-Hilbert action depending on this big G. And what you find, and then what you want to do, subject to the Cluser-Klein constraint, which is that nothing depends on x tilde, and then you find disaster. Does not work. And it's very easy to see why it doesn't work, which is that you will not obtain a field strength for B. And the reason for that is that you've already seen, what you get is, with the Cluser-Klein ansatz and Einstein-Hilbert, is that you get a field strength for D vector fields, which doesn't have the right symmetry properties because, well, it doesn't have the right symmetry properties. Okay, does not work. Incorrect. local symmetries. So at this point you give up and you go, there is no Kaluza-Klein lift of Never-Schwartz supergravity combining G with it. Or you say, I want there to be, and I just need to change my notion of geometry. Yeah.
May I ask a very naive question?
Please.
In this context, you have gauge transformations of gauge transformations.
Absolutely.
And you've been ignoring them, I guess, deliberately.
No. Oh, well, okay. I've been ignoring them in this talk. They are very crucial in what happens. I mean, we're going to come to more about the local symmetries later. It's very important you have the ghost for ghosts. And in fact, I'm coming on to discussing the constraint system. And this is a very important part. I will come to that.
But isn't the problem really that the analogy doesn't really completely work, because up there you have a metric on a bigger space that's really the total space on S1 bundle, right? While here you really have a germ, so the extension of your space was something.
That's
it's
right.
not really. So up there the
So this doesn't work, and nobody's now surprised because Christian completely understands Juleps. Nobody understood Juleps in 1980. Well, somebody might have understood Juleps in 1980, but so now what we do is we go, okay. What we then need to do is change our notion of geometry, and actually we need to change our notion of diffeomorphisms, and so on and so forth. But, okay, so we got that. So in other words, we persevere, having decided that Riemannian geometry doesn't work. So what you do is the following. To form the action, you just demand that the 2D action will equal the supergravity action if there's no dependence on x tilde. I'll come back to that. And then you ansatz an arbitrary Lagrangian that is second order in derivatives, and then put I here, AI, you've got all the ways that you can contract a two-derivative term with the metric and its inverse. So there are about, I think, 6 terms. I won't write down all the index structures. You write down all the index structures that are allowed for two derivatives in G, give a coefficient for each one, and then you impose this constraint and use that to find the set AI of coefficients such that this is true. Okay? And now you've got the equivalent of the Einstein-Hilbert term for your theory. It's not very geometric, but it gives you an action for G.
We probably should mention that G itself is a constrained object.
Yeah. Well, yeah, because it's fixed in this form. Let me say some more. I'll come. I'm fixed in this form. Now, but then that's fine for the action. But what about these local symmetries, which have been one of the key parts of how we're doing this game? Well, so now what we're going to do is introduce a generalized Lie derivative and what we want to do is use that to generate ordinary diffeos and the gauge transformations for long forms. And it's defined the following way. It's generated by a 2D vector u acting on some vector v, and it's given by the usual Lie derivative, which is L. This is the usual Lie derivative, plus some, you allow some deformation of this as follows. where y are a set of constants which control the deformation of the algebra. So at the moment, I've not said what y is. I'm just saying I will deform the algebra of diffeos and then have this deformation term controlled by y, and I want to fix y in order to reproduce my local symmetries. So that's what you do. I keep on expecting forward.
So y for yellow?
Y is, so I actually introduced the Y tensor, and I think it was because I ran out of letters or something. It's definitely not for Yano. Why did we call it Y?
Wasn't it Oxygen?
No, it was definitely Y in what we did. I should say that there's all sorts of other people who've been working on this. Charlie, who's here, did relevant work. We didn't have a reason to call it Y. Sorry. Now, so you've got this thing. You're just proposing this as a new diffeomorphism. It's a new local symmetry of this action that I wrote out here. And the guiding principle is, under some constraint, which we wrote down, we will reproduce the things. So to make that work requires y, ij, kl to be given by eta, kl, where eta, ij, is an ODD structure. So now you've got something new, which is that in order to reproduce the local symmetries, you've doubled your space. That's not enough. To write down on the right symmetries, you're required to introduce a structure on your space, which is an ODD structure. You do. So why is this? And then you check that the algebra should close. Some bracket. Turns out that this is not the usual bracket, but a bracket. But actually, it does not close. It closes up to some terms which are proportional to some stuff which I'm not going to describe. So then,
Is eta arbitrary or is it constant?
now eta is this. This is the crucial point. You've had to introduce a structure on your space. You're changing your geometry because this is now an invariant tensor of your space. And then this then becomes your new constraint. Let me write it like this. On acting on anything is equal to 0 is the constraint. Which in terms of, I think we're calling x and x tilde, is basically dx mu dx tilde mu is equal to 0. So this is obviously solved by dx tilde dot is equal to 0, but it's more general. So our Kaluza-Klein ansatz was we add dimensions and we have this constraint. What we discover is that in the full theory, I mean, it's like going to 5D gravity, you then look at 5D diffeos. What we then look at is this, is we've got this new algebra, and we see its closure does require a constraint, but the constraint is this thing, which is obviously solved by the constraint that we started with, but it's more general. Yeah.
So that term with the y dj acting on U,
dj on x and u.
D on U, yeah.
So the whole thing is algebraic on v. The whole term,
No.
the whole term, the whole second term
The second term is
is algebraic on v.
yeah. But you've still got the term now.
So we click on formula or mass or something. Analysis. Using the other conformal structure, you have a term. So it's the other mass.
Let's talk later. So Simon had a question.
Yeah, just maybe the way you communicate it for people unfamiliar with the subject, maybe not very clear. It's not really not the operator eta, ij, partial I.
Yeah. I mean, I've not put in U's and V's here.
Yeah.
And it's actually some complicated thing with other U's and V's and all sorts of things contracted and another eta and all sorts of stuff. So there's a part like this and then there's other stuff and indices contracted. It's not important.
Each pair of fields that you put in these two fields. But it should be zero. It's not a
No. No, eta. What should be zero?
No, I just say you should insist that you have these two dots. Like, so
Oh,
that
yeah.
You put pairs of fields in there.
Yeah. Okay. The key point is you want this constraint. In the end, this constraint. And then there's all sorts of indices get contracted and it's a mess. And as we go higher up, it gets more of a mess, but we don't care. It's always this form. Okay. Actually, I should write it with the y tensor. Okay. Now, so now that we've done that, we can ask ourselves the obvious question, what are the alternative choices of section conditions? Sorry, I don't say what that is. What are the alternative choices of solving this constraint? So I set the thing up by removing x tilde dependence. The obvious other solution to this is I remove x dependence and keep x tilde. If you do that, you again get the same thing of the d-dimensional supergravity with ns form. So I have two choices, both which are sort of mutually, I can't do both at the same time. I can remove x or I can remove x tilde, and in both cases I arrive at the same action under that reduction.
Why can't you have both at the same time? I mean, you get something trivial, but like it doesn't follow.
Okay, okay. I forget I'm talking to mathematics. I can have nothing depend on anything at all, and that's allowed. Thank you, Mark. The trivial case is allowed.
It's actually less trivial than you may think if you, in the context of Kaluza-Klein, when you split it up into some external coordinates and then internal coordinates that are doubled, the case where all the doubled internal coordinates are truncated out, it just brings you back to standard dimensional reduction, which is sort of the case that makes manifest why you get the O little d comma d in standard dimensional reduction, which in conventional computation is just sort of a miracle. Here it's manifest.
Yeah. Okay. So now that we've got this, we follow our Kaluza-Klein nose, as it were. And hopefully now I can go a bit faster. So it's not enough that I've got supergravity. I'm a string theorist. I want the electric charges in the theory. So the electric charge of this supergravity is given by the integral of star h, where h is dB. And following through this sort of calculation, and then you can actually find the precise solutions, this will be P x tilde mu. So what does this mean? It means that if I have a null wave pointing along the x tilde direction, so maybe over here, I'm going to write a few things. Remember, we've got xi is our level space. I've got coordinates x mu, this wacky space, x tilde, and x mu. And now I'm saying, find a solution with momentum along some particular x mu, along some particular direction in the x field. So the first thing, right, so this will then give me an electric charge. An electric charged object with respect to B mu is the fundamental string. And previously, I just had a momentum x5, that gave me an electric charge. I've now got to specify which x tilde. So it's a fundamental string aligned along this direction, x, u. Okay. So in this space, which is our ordinary space that we think of, the momentum along here will give me a string aligned along there. Okay. It's half BPS, which means that the charge will equal the tension of the string. Tension. Okay. But from a 2D perspective, it's actually null. So in double field theory, strings are massless, tensionless objects that are just null waves. Okay, so we've done that bit. But electric charges we decided were not enough when we do Kluser-Klein theory.
Sorry, why did you say it's tensionless? The tension equals...
So this is the tension from the point of view of the reduced theory in this space.
Why do you say it's a wave?
Yeah, so what I did not show is that actually I say this thing like momentum, but I should actually construct a solution in the two-dimensional theory that carries momentum. So the solution that we found is actually a null wave. It's basically a PP wave solution. And it's a PP wave solution that would be ordinarily used in GR, but pointing in the x tilde direction. And then you can show that solves the double field theory equations of motion. So by construction, it's done with a null wave. That we then reduce, we get this. And that shouldn't be a surprise because the reduction of null objects is what gives you BPS. You can think of exactly what you do in M theory in going from the wave in 11 to the D0. And you look at the actual wave solution in 11, and then look at what it looks like, you get the D0 metric. It's exactly the identical thing, but you get the fundamental string.
So when you say the 2D theory, you're in fact finding 2D.
So, sorry?
When you say the 2D theory, you're in fact finding 2D. Oh, you just said
Right.
D equals 2.
No, not D equals 2, no. D is really going to be 10.
Okay. D is 10, D is back 5.
And then we're compactifying. Well, we're back to that question. At the moment, I've not made anything compact and there's been nothing global. I must compactify if I demand electric charge quantization. Then I require that x tilde is a circle. But that's the next step. But now we're going to go even further, which is I should also have magnetic charges. Okay. So far this has all been local, and I've not really taken into account the fact I could do some twisting and have this x tilde space be fibered over the x space. So fiber this over this instead of just having it as a direct product. And that's what we need to do to construct magnetic charges. So, of course we can do that. So now we want to have magnetic charges. So now what we want to do is take this space, which is a d-dimensional space, and instead of having a product space between the two, twist this over that. But we don't need to do the whole thing if I just want one magnetic charge. I can just twist one of these circles over that and do exactly the Hopf vibration I did before. Okay? So now do the Hopf vibration, but now take x tilde, some particular x tilde as the Hopf fiber. Okay. And note that when you're doing a Hopf vibration, there's no actual dependence on the Hopf fiber in the metric. So you've got this additional dimension. Nothing depends on the additional dimension, but you're twisting the additional dimension round. So you're still doing something with the extra dimension, even though nothing depends on it. When you do that, you get the magnetic charge, G, the interval of H, which I think will be appropriately called the Dix and the Dowdy class. This is in the case where D is equal to 10, as you say, which is the string theory case. And this implies the NS fiber. So again, it's not just, I mean, here I've given the topological things. You actually find basically the Grove-Sorkin-Perry monopole I put in with the fiber being given by a particular x tilde. And then from the reduced perspective, that Kaluza-Klein monopole is the NS fiber.
So the solution depends on both x and x tilde?
No.
X tilde independent?
It's x tilde independent. X tilde is the Hopf fiber. But crucially, the solution doesn't actually depend on the Hopf fiber. But the Hopf fiber is still doing something. It's the thing that's twisting.
Yeah.
But at no point does the dependence of x tilde appear in the metric. And that's the crucial part, that you have this constraint, and then you think you don't get anything new. But you can still do this twisting of the space and still not have x tilde dependence. So, yeah. Yes, Mark?
You said you can do this for one of your coordinates.
Yeah.
In principle, you can do this for any of your coordinates.
Yeah.
Can you combine them and do like a torus vibration?
Yeah. So if you do one of them, with the fundamental string, which coordinate I chose to put momentum along was data. And that gave me then the world volume of the string. Which Hopf fiber I take here then also gives me data and tells me the orientation of the fibrane in the other space.
No, I mean, like, can you take two coordinates? Right, you didn't.
So that's one fibrane.
Yeah.
But now you can say, what if I did two of these fibers?
Right.
And then twisted them? Well, that would then allow you to have intersecting fibranes. That's why you've got to understand the role of why I've chosen one first.
Right, sure.
And then you'll get things like this of intersecting fibranes. Because it would be sort of sums of magnetic fluxes, but they wouldn't be the same magnetic flux because the transverse directions will be different. And you've got to do some basic Poincare duality to work out what should the world volumes of the fibranes given the data of which is the Hopf fiber. You can probably do more complicated things too. Yeah. You don't worry.
Is that really the right explanation? Because x tilde, after you choose the T-duality frame, you want x tilde is part of your space-time?
It's not part of the space-time.
Okay. But if I choose the T-duality frame, I know that the B field belongs to the Jerk, and the Jerk is over S3, and S3 is part of the space-time. So that's a contradiction.
Well, no, be careful.
Okay.
This S3 does not contain the S3 of which this is the Hopf fiber. I've got more than one S3. Because otherwise it wouldn't work. Which is, I think, what you're pointing to. The S3 that this thing is integrated over, this S3 is not the thing I've done the Hopf vibration.
Oh, okay.
That's just because I've got the appropriate codimension of the fibrane is that I've got S3, and I've got an additional Hopf vibration, which, I mean, strictly speaking, is in the S2 in there. There is some subtlety which you spotted, which I was hoping you wouldn't, which is actually Christine's made me into an honest person. Is that really,
Sorry.
really, this is problematic because and what I should actually have done, I do need an additional transverse isometry. So I can integrate H over S2 cross S1, and then really H is equal to F wedge d theta. That I can always do, and then this F I generate with Hoff vibration. So really I'm making the Dixon-Medalli class, which is H3, out of H2 wedge H1 of S1, and that I can do completely kosher.
So why do you need the S1 times S2? I mean,
It's really what Christine's talking about. The Kaluza-Klein monopole solution I described does the Hoff vibration where there's flux through S2 of a two-form field strength. And then I can turn that into a three-form field strength and give me Dixon-Medalli class. Let me write this as a three-cycle. By just saying, if I've got an additional isometry, so I can then put a leg on d theta with no dependence on theta, and then I can make H3 out of H2 out of the monopole.
so, okay, from my perspective, would I say that you've got a harmonic function here because it's coming from and that harmonic function is like 1 over R.
Yeah.
So it's not an NS5 brane in the transverse R4.
Yeah. It's an NS5 brane on R3 cross S1, where I've smeared over S1.
And you have to do that.
If I'm complete, I have to do
If you're an honest man.
I can definitely do it that way
Yes.
quickly,
Right.
because I then just lift to the Kaluza-Klein monopole, and it's all kosher. I would say people like open questions. It's an open question to me whether I have to do that or whether I can really do this with an S3. But I think you're perilously getting close to what Christine was worried about, which is geometrizing the jerk. Try saying that later. Geometrizing the jerk is what you're required to do to get the S3. But I can do it easily if I just have this additional S1 and then smear. And then I'm absolutely kosher with the equations and I just embed the Kaluza-Klein.
Is there like an interpretation for that? That somehow you have to cut a circle, you have to have a T? Otherwise, you're really in 10 dimensions. Right?
Yeah.
And then I don't expect a T to out.
Yeah. Well, exactly. So then things can happen. Once I've got that, lots of things can happen. I don't know if I have to. I'm just saying it's easy. I would like someone to do this for me.
It's an open question.
An open question. This is so. Rachel, you said you wanted an exercise. Do this for S3, not where I've done it for S2. Good. Right. Okay. So, wow, time is flying. So then, so we've done this. We've got the magnetic thing. We've got the NS5 brane. It's the Kaluza-Klein monopole. And so let's look a little bit about the structure of this. And T-drives. So as I said, we had this constraint, which we wrote down, and we had this eta, the ODD structure that was present that you required in order to define the symmetry. So what we really need then is that this is very analogous to the situation in geometric quantization. So this is analogous to geometric quantization. Where we have a 2D dimensional space, and then geometric quantization, it's equipped with a symplectic form. And crucially, we are required to pick a polarization which defines a Lagrangian submanifold which is, of course, d-dimensional, it's half-dimension, maximally isotropic. And then all functions then just become functions of the Lagrangian submanifold, and then we drop all dependence outside of that. So in DFT, this is the same. What we have is, instead of a symplectic structure, we have an ODD structure. The so-called strong constraint, which I wrote down, which comes about in order to close the algebra, then tells us that what we need to do in order to pick space-time is to pick a Lagrangian submanifold. So in DFT, we have our ODD structure. And again, we choose a polarization which basically solves the constraint. And then space-time is the Lagrangian submanifold. Now,
And where the symplectic structure comes from, it's just this 2D dimensional.
yeah.
You need extra structure, I suppose, with respect to just metric.
Well, no. So there's no in picking this. There's no metric. It's this ODD. It's this eta, which is the constraint. So that's like, if you like, the equivalent of the symplectic form. It doesn't use the metric.
So this is more of an analogy rather than technically precise.
Well, that's a good question.
I mean, at this level, it's clearly just an analogy.
At this level, it's an
Otherwise,
analogy.
I mean,
But but let's go through what one actually does in geometric quantization, and I think the analogy can be made more and more precise. So, I want to first do alternative choices, and then remind me if I don't say more.
Okay.
Because Now, for an arbitrary spacetime, the choice of polarization is canonical. I'll explain what I mean by that. So, by arbitrary, I mean no isometries. So if I've got this 20-dimensional space, which is my 2D space, I then say, you know what, I want to embed an arbitrary 10-dimensional space-time. Well, you can do that, and then the Lagrangian submanifold will be given by that 10-dimensional space-time. And so you've not really done much. You've just embedded this 10-dimensional space as the Lagrangian submanifold in this high-dimensional space. But now, if there are isometries, And let me call it z, in the z direction, so the coordinates z, which say are isometries. Well then, dz acting on all the fields will equal 0, and dz tilde acting on all the fields will equal 0. And so there is no canonical choice of the Lagrangian submanifold. It can be with the coordinates x and z, or x and z tilde. So space-time could be x with z, or x with z tilde. Since the space-time doesn't depend on z or z tilde, both are good choices. There's no canonical description. So I now have an ambiguity in my choice of Lagrangian submanifold. That ambiguity is T-duality. So this is the first time I've mentioned T-duality in a talk on double field theory. So normally people begin with T-duality, and I think that caused some confusion early on. Because people said, how can you have T-duality manifest if there's no isometries, etc., etc.? Because the ODD that was present in that structure was to do with local symmetries. That was an ODDR, and it was local. This is now saying, when I say, what is the space-time in the two-dimensional space, if there are isometries, there is an ambiguity, so now I have a Z2 ambiguity in Lagrangian submanifold. This choice, as it were, is T-duality. And then you can show that if you take that generalized metric and then you identify space-time to one or space-time to the other, you'll derive the Bush rules. Any questions about that?
So Z2 is Z mod 2 is like...
No, I'm just saying I've got two choices. And then go back to the I'm trying to be a mathematician. It's not helping out, you know. This.
No, that's
two
fine.
choices.
Just to clarify, could you please write symplectic structure to which you refer when you
no,
talk about
right.
Lagrangian
No.
in
So,
components?
so.
I'm a bit confused.
Right, yeah, I understand. When I'm saying polarization, so normally when I do a polarization in geometric quantization, I have a symplectic structure, and the symplectic structure is such, the polarization is given such that the fallback to the Lagrangian submanifold and the symplectic structure is equal to 0. Right? So here, I'm using the ODD constraint, which is the fact that I have eta by j, will also define for me a Lagrangian submanifold, and that's my isotropic subspace. So it's not particularly deep, but actually eta will also provide for me a Lagrangian submanifold.
Okay.
Yeah.
Can I just comment on this point, because you do have a symplectic structure here. When you talk about a polarization,
Yeah.
you're talking about taking the tangent bundle
Yep.
and splitting it into
Yep.
two pieces. Now that defines an endomorphism of the tangent bundle which squares to 1,
Yeah.
and you can compose that with your eta, and that's a symplectic.
Yes. Yes.
Or an
Yes.
almost symplectic structure.
Yeah.
It's a symplectic structure on the fiber, right? In Z space.
No, it's a symplectic
You have like
structure.
tangent plus tangent, and you identify tangent with cotangent, and you have
No,
fiber.
it's on the tangent bundle. You split the tangent bundle with this k, but then the omega you define by composing the endomorphism. of
Yeah, I
the
understand what you are saying, but I want to just complement the implications.
Well, I mean, we can discuss. For practical purposes, you just need to persuade yourself that you can pick a Lagrangian submanifold given it. And I think there's all sorts of ways.
So this is what people do with this parapermission.
Exactly. That's my next comment. Was that which is related to what to Olaf's question, which is to what extent is this analogy with geometric quantization analogy, or what way is it precise? So indeed, your complex, well, if the space was complex and then you have a symplectic structure, then it becomes paracalar.
Well, in general, paracalar is one of the simpler.
Yeah. And then, yeah, so I've got the symplectics of paracalar. Yeah.
Can I just be totally naive with no fancy language?
Yes.
What you mean is if I'm in 10 dimensions, so I've got 10 and 10 tildes,
Yeah.
and one of them's compact, like x10 is compact, then I've got a choice as to whether I choose x10 or x10 tilde, but otherwise I would choose x0 to 1 to 9.
Yeah. That's the thing. But I think to the mathematicians it is interesting that the structures that allow you to do this do fit into this. I mean, I'm aware of this paper by Weismann, where he constructs essentially the geometry of paracalar geometry. And so really what Weismann did was to take this, what we've done here in very mundane language, and then embed it by indeed identifying a symplectic structure, and he had also a complex structure. Then it was paracalar, and then use essentially the intuition from geometric quantization, which is where you're doing symplectic geometry. And then things like the generalized Lie derivative and so on are very natural, and then they'll also give what's called the Lie algebra structure, which I'm sure people know more about. So, but yeah, the more down-to-earth ways they go on here, so I've got an ambiguity, I can pick it. But it's crucial that there is this sort of structure there that gives you a sort of well-defined notion of what you're doing with the choice. Now, to go further with Olaf's question, which is in what sense is being more precise, in the geometric quantization, one of the key things and one of the problems is when you change, for those of you who don't know, in geometric quantization, you have a phase space, that's a symplectic structure with x and p. And you construct wave functions, so you're constructing a Hermitian line bundle over a symplectic space. And in principle, they will just depend on x and p, and then your polarization then restricts the wave functions down to the Lagrangian submanifold of x or p. So, one of the interesting parts of geometric quantization is that when you decide to pick one of polarization, say you pick x, you then have what's called the metaplectic correction, which tells you how you then move over to choosing x of p. And as part of that, what you need to do is define the measure on the Lagrangian submanifold of x compared to the measure on the Lagrangian submanifold of p. And when you do that, that then requires some extra jiggery pokery, which is where the fun is in geometric quantization. And this is exactly what happens in T-duality when you shift the dilaton. Because the dilaton gives you the measure, and then when you change from in x space to x tilde space, you've got to shift the measure by a volume factor. And so the shift in the measure on the volume of the Lagrangian submanifold in DFT is taken care of by the dilaton transformation.
What space does the dilaton give you the measure?
Right, so this is the point. There is, I was never going to mention the dilaton, and I've just done it. So, because it's this extra little fun factor of measures. So you have a dilaton doubled space, which is in my D, called D, and then you relate it to the usual dilaton, say an x or x tilde with a shift. And that shift is what you would expect, actually, the sort of thing that happens in geometric quantization when you move from shifting between x or p space. There is more if you're careful. If you look at the string partition function, you get what are called co-cycles, which are phases in the partition function, which also match over to the e to the I pi shifts of the metaplectic correction when you do geometric quantization. So it can be made actually more precise than you think, which is probably related to Richard's question, that hidden in there is a symplectic structure.
So you would say that the section condition is not quadratic, but linear.
Yeah. It's picking the Lagrangian submanifold. Right. It's a disaster because this was about EFT and DFT, and I've not even finished the DFT.
I think we asked you a lot of questions, so we sort of had the discussion.
So we've got,
so you can take more time if you.
So I think I've got 10 minutes left from, that gives me the hour and a half.
15 minutes.
15 minutes we can do EFT. But Olaf and Henning here, it only took them 15 minutes.
Well, I think perhaps we can take more because
No,
we have a lot of questions already.
No, 15 minutes is good. Let's not overrun. Never overrun. Okay, so this was the comment on what T-duality is. That what we're doing when we're doing this geometry is it's a geometry with equipped with a structure, in this case ODD, which can then also be extended to symplectic. And now I want to, before I move on to EFT, I want to say what else you can do, because at the moment, my string theory colleagues might be feeling critical of me, because in the end, what have I done? All I've done so far is rewrite supergravity in the NS sector, and then I've managed to tell some mathematicians something about various things. I've not actually learned anything in string theory or supergravity that you did not already know, in fact very far from it. So let's now try and learn something new, or at least could have learned something new, but in the end, this will just be a very quick way to get something that's a very hard calculation in string theory. So this is what. So before I fill this in, I think there's something important to realize that the x tilde coordinates that I have are sometimes called winding low coordinates. The reason for that should now be obvious, because when I actually put momentum in those directions, then I end up with a string that's wound in that direction. So it's, in some sense, it's conjugate to wound strings. Okay? And when we do this T-duality, it's basically swapping winding states with momentum states. So really, once we've gone through the business of identifying the fundamental string and seeing that the x tilde coordinates, the coordinates you add, are associated to wound strings, we can now use that information to learn about string winding modes. So let's go back to the NS fibrane. I've not written out the metric, but it exists. And in all of these solutions of branes, there is a harmonic function. Say harmonic. H, which is the only free function in the theory, and it obeys the equation, say harmonic, you allow delta function sources. Okay. And so typically you solve this so the whole brane solution comes down to solving one harmonic function in the transverse space. So I'm obviously not depending on x tilde here, I'm just depending on x, this is the usual thing. But now I'm going to do a series of steps. I'm going to introduce an isometry. And compact direction. So that this previously here was the Laplacian on R4. So that now, instead of R4 being the transverse space, I'll have R3 cross S1. And then, so that's not much, and then I just then have this then become a three-dimensional thing. Done nothing. Done nothing. But now I'm going to do something. Well, I've got this isometry. Radius r. I'll call that coordinate theta. I'm now going to allow to have dependence on the winding mode coordinate. So I will localize it in the x tilde or theta tilde direction. So I started out with an ordinary brain. I then smeared it, so I've got a brain with an additional transverse isometry. And I can solve that, and I've not done anything new, and people did that in supergravity. But now I will say, what happens? I can obey the strong constraint. I can obey this constraint and allow myself to have a solution that is localized, meaning has delta function support in theta tilde, the winding mode direction. So now, localize in theta tilde, which is the winding mode coordinate. So in other words, I'm now allowing the brain to actually sit somewhere specific in that x tilde space. So now I solve R3 cross S1 for the harmonic function with a delta function of R as before, but now depending on theta tilde. So you just solve this harmonic function equation. Right? So this is an exercise that you solve this. And you will find that H of R theta tilde is equal to this really rather nice function, H, showing R over R. I apologize for writing this out, but it's sort of revealing what can happen. Cosh R over R minus cos theta over R. So I get some function. This is a complicated function, but it's a function I arrived at just by solving this harmonic equation. It then turns out that this can equal 1 plus h over 2 r sum over k e to the minus k r over r plus I j over r, and this are the worldsheet instanton corrections to the NS5 brain is calculated by Davidson. He calculated it using non-perturbative effects in gauged linear sigma model. This is a hard calculation. Took Dave 6 months to do it. You've got to come up with the right gauge linear sigma model. You then calculate the instantons in the sigma model, flow to the infrared, come up with corrections to the Riemann tensor, then read off the metric. And you get this lovely instanton form, e to the I, sum over all instantons, And all I did was solve one harmonic function on R3 cross S1 in DFT. So it's the fact that after going through all this mundane stuff, we've identified the x tilde space as the coordinate conjugate to winding modes. And so now when we localize our solution in the winding mode space, we will obtain functions that depend on those, and they will give us string corrections which will give us the full instanton stuff. So Dave did find this before DFT. But I think when people ask me what is DFT good for, well, people know instanton calculations are hard. I can now do it moderately quickly.
But didn't he, in his David Town's calculus, use some T-duality structures in GLSMs? I mean, this NS5 going background and this, how does it work?
Yeah, it's unclear to me how much he uses T-duality. I don't think he needs to in his calculation, if I think back. He writes the gauge linear sigma model. T-duality then manifests in that sigma model.
Yeah, yeah.
But it's not that he uses it to generate the result. But it's true that you start out with a space with an isometry. And then the localization happens through the presence of the string corrections. You can decide how much you're using T-duality now or not. But you're doing a sigma model, so it's there. So I was going, right, I'll now, time's going up, but I'll get a bit hand-wavy, it wasn't already hand-wavy enough. So I showed that for the NS5 brain we can do this. And then I have a single winding coordinate fibered over the base. You can then start to play more games and fiber in more interesting ways, and then you will generate more what are called non-geometric fluxes of the sort that Brian Wecht and people found. And this gives rise to a whole host of exotic brains, which naturally emerge as brains in string theory that do not have supergravity solutions. They exist because we can localize in winding mode space or have twists of winding directions over others, and this gives a whole spectrum of exotic brains. So this was under what extra. Let me write 5 minutes on exotic brains. That was my most recent paper. So, under what extra? Well, I've got this calculation of including winding modes. And then I had the NS5, and that was okay. That was already one winding mode fibered over a set, an ordinary space. So there is a famous exotic, or called non-geometric fluxes in string theory. And this was, I mean, to my knowledge, I think Brian Wecht and others did this first, where you start out on T3, and then you have an NS flux, and you do a T-duality, and then you get what's called a geometric flux. That's just the flux given by dB. That's the ordinary geometric flux. That would be the flux of a twisted torus in geometry. But then you can keep on doing T-dualizations, and then you get what's called Q flux, and then you keep on going, you get something called R flux. These do not have good string theory representations, but they naturally arise in EFT from having twists of winding mode coordinates in a more general sense, or over a winding basis. And then there will be branes, or source and couple to these fluxes. And these go by the name of exotic branes. And they're highly non-perturbative. They have tensions that go like 1 over gs to the 4, 1 over gs to the 5, etc. So they're enormously non-perturbative objects in string theory. We now have explicit solutions in DFT and actually in EFT for these branes as honest solutions patched together using the local symmetries.
What's the dimensions of these branes?
What's the what?
Dimensions, space-time dimensions of Wolfram.
Yes, so they're normally a low codimension, 1 or 2. And that's why you often don't see them. So they're often codimension 2 objects, and very simple ways, things like a fold, you then have a monodromy, and then you come back under T-duality or under U-duality transformation. So Misaki Shigemori and Yandabora, big review of this. But there's a whole spectrum of branes that we normally ignore. EFT gives a good global and genuine solution of these things. So I'm now 5 minutes over. That was the end of DFT. I'm going to write one equation, one set of things, and then I will end. So once you've done it for DFT and you've realized how you generalize from Kaluza-Klein theory to DFT by having additional dimensions and extending the local symmetries, in EFT, what you're going to do is the same thing, but with higher forms. So EFT is we just do the same thing, but now we've got the metric, we've got a 3 form, we've got a 6 form. We want to combine all of these, and I'll just show you where the slightly unusual nature comes from. Because the variation of C3 is equal to D of a 2 form, then the natural thing that you're going to extend coordinates by in order to have a generalized diff is that you will have your ordinary coordinates, and then you'll have, if you like, 2-form type coordinates that will correspond to forming a vector to make the 2-form transformations of C. And then you'll have 5-form coordinates that will correspond to the gauge transformations of C6. And then you might need some more in higher dimensions, which I don't want to go into for now. So now you play the same game. I need to now extend my space with these coordinates. I combine these into a generalized Lie derivative exactly as before, only now the Y tensor will not be an ODD structure. The Y tensor will depend on the number of dimensions and will take values in the exceptional bubble. There's representations of invariant tensors for exceptional groups. And that's the origin of the exceptional geometry, is that adding in 2s and 5s always gives you representations of exceptional groups. But you follow the same thing. The local symmetry thing I wrote was the same. The constraint was the same, which arises from the closure of the local algebra. But then we need an exceptional invariant structure on the manifold, and then we need, instead of a special Lagrangian submanifold, we need some other submanifold of lower dimension. So then you've got to generalize, in some sense, symplectic geometry. And I think some people are still working on that idea. Thank you for your patience. Thank you very much.
Okay, any further questions for David? He's been very gracious. Yes? So back over here when you had the ambiguity in your choice of polarization, you had these isometries, the Z. These were abelian isometries. If I take a non-abelian group of isometries, is there a way to kind of nicely see non-abelian G-duality in this framework?
There ought to be, but nobody's done it.
Right.
That is a certainly open research question, and with my ex-student Dan Thompson, we have a plan to look at that at some point. So that is a very good question.
Other questions?
So can you say a bit more about the analog of the symmetric geometry into duality, right?
Yeah. See, I don't want to mention U-duality because that's like mentioning T-duality. You shouldn't mention T-duality in double field. That's only when there's an isometry. But yes, there's an exceptional structure. So a very quick equation. The Y tensor was the deformation of the local algebra, and you end up with Y by J. Now, this is some invariant of some exceptional group or some exceptional algebra, and you end up again with a sort of quadratic constraint like this acting on all fields. So then you pick your Lagrangian submanifold as solving this constraint. Now the remarkable thing is that that does not take you to half the dimension because of the nature of these y's. So you need to look example by example, but it takes you much lower. It doesn't half the dimension. And that's what you want, because when I extend the dimensions here from x to 2 forms and 5 forms, the doubling was a coincidence in ODD because this was a 1 form. Now I've got a space with 2 forms and 5 forms. It doesn't double, you've got to go down there. Now the remarkable thing is there turn out to be 2 independent solutions to these things. One of them takes you down to d dimensions, and one to d minus 1 of different spaces. And this is like M theory, and this is like 2b. This was worked out by Chris and Chris Blaine. So there are 2 natural alternative choices of polarization in some sense, but actually differ in dimension, which is weird. Because normally when I do geometric quantization, I half the dimension and I choose another one, I got the other half. Now, the equivalent's like doing a Fourier transform and then transforming to a space, we're not even preserving the same dimensionality. So we have puzzles. I mean, you know, DFT, there are some flukes, but I emphasize their flukes, which is just the fact that the winding mode is the same dimension as the momentum. And it comes down to the fact that membrane winding is over 2 dimensions and the momentum is 1 dimension. So when you swap winding and momentum in M theory, you do not preserve dimensionality. And you see this completely, that M theory on a torus is the same as 2B on a circle, and they're the same, but they're not the same dimension, because the membrane winding is 2 dimensions, and that's 1 momentum mode in 2B. So we need to do a lot more. A lot more.
Other questions? Just a quick question. Is it clear how the harmonic function is related to instantons? Or is that wrong?
Is it clear?
Okay, you go.
That's, oh, let me ask everyone else. Was it clear? I mean, let me just say, you've got to get your head around the fact that those coordinates are conjugates of winding. Once you've decided that, it's sort of inevitable. So one of the things which is in my notes that I didn't get to, that was done before by Dave Tom. You can do the same calculation in the exceptional case and get the membrane instanton correction using the same argument. But you solve a different harmonic function. But nobody's calculating membrane instanton corrections for the for the M5. So I've got a prediction for you, but I've not got anyone to test it. So you've got one of those great things where people say, EFT, DFT, is it giving you anything new? And then I give you something new, go, how do we know it's true? That's good. So I can give you something new, but you won't believe it. Or I give you something which you know is true, and then you've not done anything new. There's a duality there.
Okay, David has given us a lot of exercises. Thank him again.